Hi, welcome to CSE351 Introduction to Data Science, and this chapter is on linear regression. Okay, so linear regression is a very popular algorithm in machine learning and is also very important for data science. A lot of problems we solve using linear regression. So let's see, like, what is it all about, and in what scenario we will be using linear regression. So let's consider that we have some points right here, n of those, and these points are in blue. So now we want to learn from these points, and we want to approximate these points so that if someone wants to know about the value of y, so let me use my pen to explain this thing. So here, assume that we are given these endpoints, and the data is in x dimension. There's only one dimension which is available to us, so I will call this x. Alright, so this is x and we have f of x. So what is given to us are these points, and we just plotted these points, and we can see that there is some pattern between x and the corresponding fx. So x is given to us and we want to say something about fx, which is our y. In y-axis we have fx. So let me make it more concrete by giving you an example of a scenario. How about this? Assume that we are given this data which has the area of the house and the price. So we want to find some relationship between the area and the price. So if I call it x and the price as f of x, then we want to find out some predictor for this data. We want to predict that if somebody gives me some areas, say 3500, then what would be the corresponding price? Okay, so the first thing that we should be doing in these kind of problems is to plot the data, and here the data is pretty simple. It has only one dimension, which is x. So this is my x right here. And when you plot this data, the price corresponding to the square feet area, then you can see there is some linear trend, and it won't be difficult for you to analyze that or reason about the fact that more is the square feet, the higher should be the price. Okay, so this is an interesting example which gives us some idea about the linear regression, that if this kind of a data is given to us, we can apply linear regression where we will try to approximate this data that we have by finding out the best line that fits this data, something like this. Alright, so we'll have to find out the equation for this line, right? Because once we have this line which is approximating the data that is available to us, which is the price on the basis of the square feet of the area of the houses, then if somebody is asking like what would be the price for 3500 square feet area house, then what we will have to do is, this number is right here, we will try to get that value from this line. Alright, so that's what linear regression does. So back to my first example, this is more general. We'll be given a collection of endpoints, and the example that we are considering is very simple, just the way we had the house price data. There's only one dimension in the data, okay, and like the square foot area is only available to us, and using that we are trying to predict the price. Okay, so what we have to do, we need to find a line which best approximates these points. Alright, so if you see, then yeah, this seems like a good line which is approximating these data points, because this is passing through the middle of these points that we have in the data set. Okay, so now there are a lot of questions that you might ask, that why are we trying to find a line? Why is this function linear? Why not some more complicated one? So the answer to that would be yes, we do have other approaches also, we do try to fit other functions as well which are non-linear. But this linear function, surprisingly, it gives very good result in a lot of situations. Okay, so one of the reason why you may start with the linear relationship is that it is very easy to understand. All right, it is easy to understand, and it works in a lot of different cases as well. Example, we have some some examples like where we can see that linear regression would work perfectly. So as an example, think about the income. So income grows linearly with the time you work, right? So you should agree with me. Yeah, think about the scenario where we are working on contract, right? So the price is say $35 per hour. So that's your that's how you're getting paid. You are working on hourly basis, and the rate is $35 per hour, right? So you can see this linear trend that if I'm working for h number of hours and the rate is $35, then you can figure out my salary. All right, so this income kind of a thing that you're looking at on the basis of what I'm giving you as an example, it's not difficult to visualize that this can be easily approximated using the linear regression or linear function. So that's one of the common case. Housing price, right? So I just gave you the example about the house prices based on the square feet area. Okay, so that is also um, that will follow linearly with the area. Okay, we will have only few exceptions, but mostly it should follow linearly with the house price should follow linearly with area. If you want, you can add more features. So right now, sorry, in this case it's just two-dimensional for the reason that you have x on the x-axis, which is your square feet, and you're predicting or you are finding out fx, which is the price on the y-axis. You can also add one more dimension to it. That could be a number of bedrooms that you have, number of restrooms that you have, whether you have a pool or not. So the point is that you may add more features, but just and it will work perfectly fine. The linear regression will still work. But the reason why we are taking only one feature here is just to explain to you the concept behind linear regression. Okay. All right. So there's another example which relates with your weight increase, right? So if you eat more, your weight will increase more, and if you fast, probably you will lose some weight. So there are also, if you do this kind of experiment, like feeding people with some amount of food and then monitoring their weight, probably you'll get a linear relationship, and the case of linear regression might be a good fit in that data as well. Okay, so now there's this interesting thing about the statistician's rule. It says that if you have any 2 points, this is one point, doesn't matter the other point, you pick the point anywhere in space. Let me put a point right here. Then we can draw one straight line fitting these 2 points. So as long as you have any 2 points in space or two data points in the space, you're perfectly fine. You can draw a line between these two. But as and when the number of points start growing, or the number of data points that you have grows, it's very difficult to find one line that passes all those points, right? Let's go back to this example. We have a lot of points, so we could not find one line that is passing through all the points. Back to the first example, same as the scenario. We have a lot of data points like these blue points, and the red line, which is approximating these points, is passing through, maybe, if you want to count 1 2 3 4 5 6 7 8, luckily, right? So luckily we have this line passing through only 8 points. But if you look at the data size, then the number of points that I have are much more than these 8 points which are luckily falling on the regression line. And our attempt is also not to come up with a line that will pass through all the points. We want to find out a line that best approximates these data points, the line that passes through the middle of all these points. Okay, so with this intuition, let's move on and see like how is this linear regression formulated. So let's look at another scenario. You have a simple case as has been in the previous two example. There is x, which is independent variable, and on x we have fx, which we are calling as y. So I may say y is equal to function of x. Okay, and function of x is something that we are trying to approximate with the help of this line that you have. All right, so assume that we found one line to approximate these data points. Now since the line is not passing through all the data points, so we have this error. All right, so what is this error? If you look at the actual value of the y for this data point, so let me draw some parallel line. Okay, so that's the correct yi, which means the this ith data point, and its y coordinate is yi. All right, that is in actual what we have, and you can drop vertical line down here on the x-axis to get the corresponding point xi. All right, so from the data set that we have, because you have to learn this line, you have to learn the approximation of this line. And how do you learn? You will learn that from the data which is given to you, the training data. So all these points that you see here, these are all training data, because on the basis of these points only you could come up with the line like this. Okay, good. So in reality, the yi is the value which corresponds to xi. But what happened, you came up with this line, right? Let's say this line is given by the function f of x. So yi is what you have in the real data, but yi hat is what you got. All right, so this is a predicted yi for xi, which in fact is f of xi. All right, so now you should see that. Let me make one more parallel line. Okay, so now this much is the error. Error means we failed to approximate yi perfectly, and we were off by this amount. We were off by this amount, which is yi minus f of xi. All right, and this term that we have for the ith training point is called the residual error. Okay, so for the ith point we got the residual ri is equal to yi, which was the actual value of the target. We also call that target sometime. Target is something that you want to predict. Alright, so target is yi, which we want to predict. It could be like house price, and xi is the independent variable, like the area of your house in square foot. So using that you will predict the target, and the error in the target is your residual error. So you can find this out. It should not be difficult, right? So we should find out this error for all the training data that we have. Okay, so now the point is that how do we evaluate a line, like whether it is a good fit or not. So we have to continue this search, and ultimately we are working on an optimization problem. Why optimization? Well, because we want to find out a line which is resulting in the minimum residual error for all the data sample that we have in the training data. Okay, so there is something called as cost function that will appear in the next few slides. So we have a notion of cost function or loss function. There are a number of terms that apply to this concept. So how do we come up with the loss function? So basically for the total loss, what we do is we square, right? We square these, well, the cost function is called least square regression, square cost function, and this corresponding regression is called least square regression. So what do we try to do for this cost function? We square this thing, right? And then we sum it up. I is equal to 1 to n. Alright, so assuming that this is the error that we found in the ith data sample, then for cost function that we have, what we do, we find this error, square it up, and sum it up for all the data sample that we have, all the data points that we have. Assuming we have n data points, then you will sum it up. And our approach should be to minimize this cost function. We also call that as J. Alright, so you will find more, you'll define a proper cost function for this, this algorithm. Anyway, so the least square regression minimizes the sum of the squares of the residual for all the points, right? So that's what I tried to do. Now you should wonder, and usually a lot of people, they ask this question, that why are we squaring it, right? Why can't we leave it like that? No square, just add it up for all the terms. Or why not take the absolute value? So if you're thinking about taking the absolute value, then kind of you got some idea that maybe taking this exact value is not meaningful. If you're saying that let me only sum up yi minus f of xi, well, that is not good, because some terms that you have here are above the line and some terms are below the line. So this plus minus will cancel up, right? So if you were off, if you predicted the point to be above or the below, then this error would kind of cancel out, right? Plus or minus. So if you take the square, then that easily solves the problem. Okay, so it will ignore the sign. If you square it up, then that is going to ignore the sign, which is a good news. And by that, it doesn't matter whether you are above the line or you are below the line. Error is an error. Okay, so it should add up. Error should not subtract. So that is something we achieve by squaring it. Now the most important thing that we have here is it has to do with the mathematics actually. So ultimately, what you got it here is an expression which is a cost, and we will have to apply some optimization on this function to come up with the best value of the coefficients for this line. Okay, so this is a line, and this line should have some form as y is equal to mx plus c. That's how we represent line in geometry. So to find out the equation of this line, we should have m, we should have c. These are the constants we'll determine. On the basis of that, the line would be drawn. So you optimize this cost function to find out m and c. And in machine learning and in data science, we call these as W1x and W0 weights. Alright, yeah, so if you square it up, then this will result in a very nice function which is very easy to work on. Alright, so this squaring gives us a very nice closed form solution. Okay, so now this lecture will involve a decent amount of mathematics. I tried my best to make it very light, and I just want you to get the intuitions out of it. So in the linear regression, we have two kinds of solutions possible. The first one is the closed form solution. So you're looking at the closed form solution right now. So this derivation that you have ultimately right here, we need W, because W is the vector. W is the vector of coefficients which we want to have so that we can approximate the line. So in the above example, the example that you have here, the W should be a vector of W0 and W1. Alright, and why do we need W0 and W1? Because using W0 and W1, this equation of y would be y is equal to W0 plus W1 times x. Okay, so we need to find out W, the vector with all the coefficients. Alright, so W is a coefficient vector that we need to find out for the best line that is approximating our data. Okay, so this result that we have, you should pay focus to the result. This result you will get after doing some, there are sets of linear algebra operations which we perform on our data, and finally we get the value of W. Okay, so let me give you some intuition like what these terms are. So when you have a data, right, so the data will come in this form. So A right here that you have would be the data matrix. The A is data matrix, and the B is the vector of target values. Alright, so assuming that someone has given me the data for the Long Island houses, right? So in the data I have the price for 1,000 houses in Long Island. So the B that you have here would be the house price, right? So it would be the house price, which is the target that you want to learn or predict. Now you should say, what is an A? What is A? A is a data matrix. What does that mean? Well, wait a second, right? If I have the number of houses as n, right? So what is n? N is the number of data points. Number of data points means number of houses that I have. Assume that someone has given me n houses, n is equal to 100. Okay, or 1,000. I initially said 1,000, so let me stick to 1,000 only. Now what is this data matrix? So the data matrix would be of the dimension n, because these are 1,000 houses, and into m, and rows and m columns. So what are these m columns? M columns stands for the m variables. Right, so example for the house price could be, if m is equal to 3, let's think of some 3 variables. So say x1 could be area in the square feet, x2 could be number of bedrooms, okay, x3 could be number of restroom. It is up to you, restrooms, assuming that these factors determine the cost. So this data matrix that I have would be of dimension and rows and m columns. All right, and then this x that you have would be our weight matrix, or sorry, weight vector, weight or this vector, or w vector. That's what we have to compute. So this x should be a w. So you will find some issues with these notations. So replace this x with w. So now when we solve it out after applying a decent amount of linear algebra concepts, finally w can be derived in this form. Transpose of this data matrix multiplied with itself, inverse of that multiplied with the data matrix itself, transpose of that, and this target value. That will give you the vector of the coefficients. Alright, and that's what we have to learn, because the coefficients will define the line. The coefficient will approximate this line. So if you're wondering like how would your price look when m is equal to 3, then your price should look something like this. price, assuming that you found the correct value of W1, W2 and W3. So here, since you have three variables x1, x2, x3, so your price would be something like this: W0, you need to find that out, and all those are coming from here. Okay, so this W0, W1, W2, W3, they are all coming from here. If you have the data, you apply this formulation, you'll get the vector W. So it will be W0 plus W1 times x1 plus W2 times x2 plus W3 times x3. Alright, so this is how you will be able to approximate the data. And if I give you any if I want to get the information about the price of a new house, then I should provide you the value of x1, which is a square foot area, x2, the number of bedrooms that I have, and x3, which is the number of restrooms that I have. Okay, so now if you want to interpret, let me clear some clutter right here. Okay, so probably you don't need this. Okay, that's fine. Now let's try to understand this expression. So the dimension of A is n to m. So the transpose of A would be m to n, right? I hope you know what is transpose of a matrix. If not, then please revise these concepts. A is of dimension n to m, and rows we have m properties or m variables we have. So it is m cross n matrix multiplied by n cross m, and this okay, so this should be then you inverse that. So after inversing also it will be m by m, so it doesn't matter. This whole, if you compute, would come out to be m cross m. Alright, so the dimension is m cross m, and if you inverse that, still it will be m cross m. Then then we have A transpose again, that means m cross n, right? So this is m cross n followed by n cross 1. So if you do all these operations properly, you'll find out that the resultant is the coefficient vector that you're getting is m cross 1. That means m was 3 for us, but we keep W0 as well, so it will have W0, W1, W2, W3. Alright, so that's what you have for W. So this W0 you'll find a little strange, but we need to keep W0 because that will serve as our intercept for a line that we approximate. So these things are a little intense, right? So you'll be fine if you just get the intuitive idea behind it. The detailed derivations and all, I believe, should be covered in some machine learning course, because it needs some background, some linear algebra background and some calculus background. Okay, so we have this result right here. Similarly, there's another result which you can obtain by using the equation of y, which is w0 plus w1x. This is again something which we are using for only one variable, right? So if you have more, then you should have w1 w2 into x2 and so on and so forth. So now if you put this in the cost function and try to optimize w, then the value of w1 that we get, which is the slope, follows this expression. All right, so if you simplify it further, then this expression will reduce to rxy, which is correlation coefficient, then standard deviation of x and standard deviation of y. Alright, so when this value of slope that you get for your line after doing some optimization, you get the final expression as rxy, which is correlation between x and y, multiplied by the standard deviation of x divided by standard deviation of y, then it gives us some very good insight in the value of w1, alright, which is the slope of the line. So let's try to understand this slope of the line. But before that, let me intercept this thing about intercept, which is w0. So how do we find w0? w1 is anyway found by this expression. Now for the best approximation, the line that you have here, it should pass through the mean. What is the mean? Through x bar and y bar. Okay, x bar and y bar is the mean of the data that you have. Mean of x coordinates, or mean of the properties of the data is x bar, and mean of the target is y bar. So this line should pass through these two values to give the best approximation. So if you put these values in the equation right here, so what will happen? It will be y bar equals w0 plus w1 and x bar, right? So from there you'll get w0 is equal to y bar minus w1 x bar. Okay, so you can obtain the intercept as well. w1 was important. Once you have w1, you can put the value of w1 here and get the value of intercept w0. Alright, now this interpretation is interesting actually. The relationship between the slope, what is w1? It's the slope of the line. How is the slope of the line related with the correlation coefficient? Okay, because we have already learned about correlation coefficient in our previous lecture. Alright, so if x and y are uncorrelated, right? So if x and y are uncorrelated, then w1 should be 0, right? It makes a lot of sense. Okay, because if you have no correlation, let me draw a figure somewhere. This is more cluttered, but anyway, assuming this is my x and that's my y, and the data is like this. Okay, and you approximated that by this line this way. So here w1 is equal to 0. Alright, so w1 is equal to 0 relates with the correlation coefficient, right? So here w1 is 0 because correlation is 0. Alright, so that is making a lot of sense. We don't see any linear pattern or any correlation between x and y. Alright, and if x and y are perfectly correlated, right, so if the correlation is 1, okay, if r x y is equal to 1, then what would be the slope? Then slope is equal to then the slope would be x by standard deviation of x divided by standard deviation of y, and rx, the correlation between x and y is 1. Okay, so that's what we mean by the second point. If x and y are perfectly correlated, then that means the slope should depend on the magnitude of x and y in their standard deviations. Okay, so now you might be wondering, like, how come this boiled down to correlation? So effectively, the formula that we have as a result of the linear algebra steps defines W as A transpose times A, inverse of that multiplied by A transpose and B again. So this has correlation covariance matrix somewhere. Alright, so all these terms that you have, these are occurring in the form of the covariance matrix. So covariance information is there in its formulation, so this is no surprise. Okay, so now let's move on a little bit towards the practical aspects from these theoretical aspects. Like when you have to do regression, linear regression, then how can we obtain better results? So there are a lot of things that we need to keep in mind when we are doing linear regression. So the first thing is that we should look at outliers, and if there are some outliers in our data, then we should try to remove those. Otherwise, we won't get a very good linear regression results. Similarly, you'll have some situations where the data may not look linear in the original features space. So we might have to translate those features into using some nonlinear functions. And then there are a few things that might arise because of the features or the target that we need to learn, and we will have to use some scaling, feature scaling. All right, and there's another very important thing that we need to keep in mind while doing linear regression, that is about the variables. So sometimes you may find few variables which are very strongly correlated with each other. So as long as the variables are strongly correlated with the target variable, we are perfectly fine. But any strong correlation between these variables is a bad news in the regression models. So we need to look at all these things because they will determine the performance of a regression model. All right, so let's see like what can happen if you have an outlier. So we have two scenarios here. So let's look at the scenario number one. Here you have an outlier. Okay, so since this line that you're getting through this optimization process for linear regression tries its best to fit the data that is given to us. Okay, so because of this point right here, which is an outlier, the line will make its the approximating regression line will try its best to explain this data point as well. And in this process, what will happen, it will tilt a little bit towards the x-axis, right? So if I remove this thing like here in this in the second figure, then what will happen, then we'll have a lot better line explaining most of the data here. Okay, but because of the presence of an outlier, this algorithm tried a little hard and tried to explain this variable as well, and because of which we did not get a better fit. Okay, so if you could remove this outlier, then you'll get a lot better fitting. Okay, and that can be explained by the R as well. Alright, so this correlation coefficient is 0.4 in the first case because of the outlier, and if you remove that outlier, then the value improves. Okay, so that's an important message. So why is this so serious? This is more serious for the reason that the residuals that we have, right? So if you remember, residuals are the error that we have. So because of the fact that in our error or the cost function, we are using quadratic of that. Quadratic means we are squaring that. So what we are doing yi minus f of xi. All right, we are squaring it. Okay, so this is quadratic, this is in terms of 2. So because of this outlier, it will change this approximation a lot. Okay, so what will happen because of this quadratic weight of residuals, outlying points can greatly affect the fit. That's what is happening here. So we should try to find out the outlying points and remove them in a principled way that will give us a robust fit. So that's a very interesting point that we should keep in mind while doing linear regression. So this is a second situation, right? So if you look at the data, then the data is again in these blue dotted points, and then we can try to fit a straight line. You can say that we will apply the linear regression in the original x and y, right? So original x and y, if you're doing and you're trying to fit a line through it, then you can see that this line is not doing well. It's not doing justice with the approximation. All right, we are missing a lot of points here. So a trick for this kind of problem is to try to fit the functions of the parameter, right? So x is the original variable that you have. Now if you want to fit this the quadratic of this x, right, so which is x square. So if instead of doing linear regression on x versus y, if you do x square versus y, x square versus y, then what will happen? Then you will get a linear regression. Then you'll get a line which will better approximate your data. Okay, so the point is that with the linear regression, okay, one more time. In the normal situation, linear regression will fit a line. Okay, so that's what you see in the screen plot. Linear regression will fit the line. Now what we can do in situations like this, we can have we can fit some polynomials as well. How? Because these features that you have, like the other feature that I added was, along with x you have x square, right? So these features you can add to your data. So if your data had just one, let me make this scenario. So our simple data was like this. You had x, and then there was the target y. Alright, and you were trying to fit the line through that. You were using the normal linear regression. But if you could add the feature like one more, x square, and then do the, we don't need any other. If you do the linear regression with these two, and the target being y, then you'll get a lot better approximation like this. So that's the message. Sometimes adding more features to the feature set helps us in linear regression, and in that case our linear regression model performs a lot better. Okay, so we can fit arbitrary polynomials including the square root and the exponential logarithms by explicitly including the component variable. So I just added x square. You can use square root of x, you can use log of x, you can use x cubed, 1 by x, and all that. And that is possible, and people use that in a lot of situations. But we need to be very careful about all these things, right? Being too ambitious would be a problem at times. Okay, so if we try too many things, then it may become intractable. So we should do these things, but with some caution. The message is that it is possible to use linear regression with the features like this, right? Like quadratic you can use for the linear regression. Okay, so what is the next issue that we should keep in mind? When you do a linear regression, you might have some issues like the range of the values that different features are taking. So as an interesting example here, so if you, for some reason you are working on a data that has a variable which is about national population, so the population would be huge. Look at this value. So one parameter that you have, x1, call it, is population, nation's population, which is a huge number. And then you can have another feature called that x2, like this, which is a fraction. Now the problem is that if you try to do linear regression on this problem in its original form, then you will have difficulty in the optimization algorithm. So we will be learning about gradient descent algorithm in this lecture itself in next few slides. So if you don't make sure that these variables are in the same range, the gradient descent will have tough time converging to the optimal solution. Okay, so what should we do? So these are some technical details, right? Step size and all. This you will understand once we look at the gradient descent algorithm. So the message is that whenever you have these variables that have different scales or different range, we should use z-score. Alright, and by using z-score we will be able to bring all those parameters in the same range. Okay, so how do we compute z-score? I hope you know that. zi I will compute as xi minus the mean of x divided by standard deviation of x. Okay, if x is my parameter, and the value would be in between -1 to 1. Okay, so that was about the scale. Then we have a similar situation we may face when we are dealing with different kind of variables. So if okay, so let's see what is this example about. Consider that we are modeling the variable y, which is years of education. All right, years of education you are predicting on the basis of the income that you make. Okay, so now this is an interesting case which you might consider. You might say that this is possible, I can do it. Income, yeah, income should relate to the number of years, because usually those people who are studying much, they get a better job and they will have better salary. But this is a little tricky. Reason being that this feature that you have income follows the power law. Okay, and power law is not a good news in modeling. Whenever we encounter power law, we need to somehow take care of that variable before we plug that in any normal machine learning algorithm. Okay, so here we are we have income, so income will follow the power law, but the y value that you have, which is the number of years somebody has put in education, will vary from 0, meaning that that guy did not go to school at all, then 12 years for high school, 4 years for undergrad, and probably 5 years for graduate, so 19 years. Now the problem is because of the power law, as I said. Because if you have those people who are earning a lot, like Bill Gates, right? So if you have a data like Bill Gates data, then it will make it very, very difficult for the linear regression to fit itself properly. Okay, so we'll have problems in dealing with this kind of data. So what should we do? Just using z-score will not help us in this case, right? Because z-score will only help when you have the variable that is probably normally distributed. So the problem is because of the income variable, which follows a power law. Then what we should do is, let's normalize this variable by using the log. Alright, so you should have got this idea by now that whenever we have power laws, taking the log helps. Okay, so what we will be doing in this case, if we have to really do this kind of linear regression, we will first compute the log of the income, and then we will compute the z-score. Okay, so these are all the topics and feature scaling. So here we are explaining the problem in the previous regression. An enormous gap between the largest and the smallest, and the median values mean no coefficient can use these features without the same point. So what we should be doing, we should replace the feature x with the log of x or square root of x, and then we can compute the z-score. That way the regression that we get would be more meaningful. Alright, so let's see what's the other thing. Now if similarly in the previous example, our independent variable, right, this is kind of x, which is our independent variable. So independent variable was following the power law distribution. You can have a situation similar to that, where you're trying to predict income. Okay, so income is again power law, right? So you're trying to predict income from a z-score variable will need large coefficients, right? So how can we get to $100,000 when you have the functions from minus that? So this is about z-score. So how can we do that, right? So this situation is different from the previous one, because here we are trying to predict the power law. Okay, in the previous case we were using the power law to predict the normal variables. Alright, so what we will do here, again the same solution. We will have to take the logs of the target that we want to predict. Now, to the last point, which relates with the correlated variables. What we should do in the data matrix that we have, we should find out those highly correlated features. Features are the attributes which are highly correlated with each other, and we should try to remove at least one. Otherwise, correlated features are not a good news for linear regression. So that's what we have here. Suppose you have two perfectly correlated features. Example being, if for some reason we have the value of height available in 2 units, right? So height is in feet, and we have another column with height in meters. So that will perfectly correlate. Okay, so this is a bad news for linear regression. Why? Because if you remember, in the formulation we are doing something like this, right? So that was the closed form solution that we looked at. So W is equal to A transpose A and inverse of that. Now in this matrix that you have, if you have two highly correlated features, then probably this will become singular, right? Singular matrix means its determinant will be 0, and in that case it will be not possible to inverse the matrix. So in a way we are going in the wrong direction if we have strongly correlated features. And when we are talking about correlation, then this correlation is between any two features, right? Not a feature with the target. If you have a strong correlation between a feature and a target, then that is a good news. And here we mean to say that the strong correlation between independent variables. Okay, so that's the explanation that perfectly correlated features provide no additional information to modeling. Okay, so there are these approaches possible. We can do dimensionality reduction. In the dimensionality reduction, we will find out the important features, and we will only use those important features for linear regression. Okay, and the techniques like PCA can be used. All right. Now, what we have looked at till now for the linear regression is a solution that is called closed form solution. Okay, so this solution of finding out W as A transpose A, inverse of that multiplied by A transpose and the vector B, this solution which provides W is called a closed form solution. But it has some problems. Okay, so let's see, like, what are the problems. As long as your data is simple, you are good, because you don't need to think too much. Just apply this, get some library which can work properly with the matrices. Probably, you know we have numpy. Using numpy we can do that. But the problem is that as your data gets bigger, right? So if you are dealing with a large system, then for the large system, that means you have a lot of variables and you have a lot of data. Then this inversion process, the inverse that you need to compute, gets very, very slow. All right, so that's a bad news. So in practice, people don't use closed form solution. They use other solutions that we'll discuss in the remaining part of the lecture. So that was one part. The other part is that this formulation is brittle, right? So this linear algebra stuff that we have is very hard. It cannot be easily extended. Okay, so that comes as a bottleneck. So what do we need to keep in mind? We need to keep in mind that this closed form solution is very elegant, concise, easy to implement, but its inversion is inefficient when the data size is complex. When the data is complex, like a lot of features, a lot of data sets, then its inversion would be tricky. And the second thing is that the formulation is brittle. Okay, so it's not very easily extendable. So what we do, we use a different approach, which is called gradient descent approach to solving the regression. And this gradient descent is very is very common. It is this approach is used in a lot of machine learning algorithms for optimization. Okay, so now we'll look at this formulation one more time because we need to understand how gradient descent works. All right, so this thing that you see here, what are we trying to do? We are trying to do the same thing. We want to fit a line perfectly to the data so that the sum of squared error is minimized. And where is the sum of squared error? Right here. Yi is the correct label or the target for the ith data point. F of xi is the predicted value that we are getting from the line, and this difference is the residual for the ith point. We want this to be minimized over all the points that we have, and this is squared error, right? So we know why did we take the squared error, because of first it will ignore the sign of the error, and the second thing is that it will result in a nice formulation which will help us in optimization. Okay, so this whole expression that you have, which is computing the error in our approximation, is given a name like J, is the cost function. Cost function which we want to optimize or minimize. This is J of W0, W1. And here again we are using a very simple scenario where it's only one independent variable we have. It's just one dimensional problem, like the square area of the house. On the basis of that, we want to find out its price. Okay, so our fx is w0 plus w1 times x. Alright, so in what we'll do, you can plug this value for f of xi. Alright, so let's see how will this work out. On the left hand side, you have the real scenario, which is x is given to you, which is x is independent variable, y is the dependent variable, and we have some data points. We want to find out the best line that approximates these data points. And how do we evaluate whether the line is good or not? We evaluate that on the basis of the error function. Error function or the cost function means the same thing. Okay, and what is JW0W1? Right here. Okay, just the square of the residuals for over all the data points. We are summing it up and dividing that by the number of samples we have, 1 by 2n. Alright, so what we have to do here, we need to find out the pair of W0 and W1 which will result in the minimum of this error function. Okay, so this is the real scenario where we want to find out the best line approximating these data points, but finding the best line means finding the best value of W0 and W1. Okay, so here we cannot change anything, the data points are fixed. We cannot change anything in the data points. We can just adjust our line in this plot. But how do we adjust the line? For improving the line or the approximation, what we should do is we need to look for the better W0 and W1. Okay, so this optimization that happens is in the space of W1 and W0. Alright, and here the example is so simple that our W0 is which is the intercept is passing through 0, 0. So we are not considering W0, we are only considering W1. So the cost function that you have here is only in terms of W1. Alright, so this is the function that we have over the range of W's, and we want to find out the best W1 which will reduce our cost. Alright, so if you look at this, then this function that you have, the JWW0 is a convex function. Right, so these kind of functions are called convex function. Alright, so a good news about the convex function is that the convex function will have only one optima, minima or maxima, and that is global. right? So that is a good news about the convex functions. So if your cost function is convex and you apply any search algorithm for the optima, then whatever optima you find, it will be the global optima. We won't have the local and global, right? So we don't have the problem of getting stuck at the local optima. Okay, so this is our cost function w0 w1 which we want to optimize. And this function you can see like this, because you have just one variable, you have only w1. But if you think of w0 and w1 together, if you want to find out the error function in terms of w0 and w1, then it will be in the form of a then it will be a two-dimensional surface, the way you can see here. It's in the shape of a bowl. Okay, and this is convex as well. So if you start from anywhere, right here, here or here, and you start searching for the local optima, sorry, the global minima, you'll always reach out to 1. You can't get stuck at the local optima. So that was the reason why we made it squared. That's the reason why we took it as the squared error. Otherwise it will be a non-convex function and we'll have difficulty in finding out the best parameters. Alright, so what is a gradient descent thing? So gradient descent is a search algorithm which we'll be using to optimize this problem. And here it is about the convex function. So the space with only one local and global minima is called a convex function. So well, there are a lot of definitions of convex functions, like when do we call a function as convex and when not, right? But the formulation that we have here is more appropriate for our discussion. So you should say that any space or any function would be would be convex if you have only one local or global minimum, would be called convex. So right here you have just one local minimum. Here also you have one local minima, so it is convex. So if I just a second, if I make some plot like this, where you have, so this is not convex. Why? Because you have this one minima here, second here, third here, fourth here, right? So these are all local minima. We may have a global minima right here, okay, but you have some local minima as well. Now the good news about the convex function is that when your search space is convex, then we can find the minima very easily. How? We will just walk down, and we walk down on the steepest descent. That's the idea behind the gradient descent algorithm that we will learn. So when your search space is convex and you are looking for the minima, what you need to do is keep walking down the steepest descent. Alright, so how do we do that? We find out the fastest direction down in such a way that we reach to the global optima as soon as possible. And how we do that? We follow the slope of that curve, and slope is same as the tangent. So wherever you are on that curve, say you are right here. Okay, so you are right here because you will start with some random w0 or w1, or here we have only w1. Start with w1 right here, but the global is at this position. So what do you do? At this point, find out the tangent. Alright, so that's the direction of the tangent. Okay, sorry, it should not go up in. If you are at this point, you will come to the tangent, right? Tangent will give you some direction, like in which direction you need to move, and in that direction you will move, keep moving, and ultimately you will converge. So that is the gradient descent thing. Alright, so when a such space is convex, it is easy to find the minima. We just need to keep walking down. Down means in the right direction. You need to minimize. Okay, and the fastest direction down is defined by the slope or tangent at the current point. Okay, so this should explain. Now, if you are at some point, right, if you are at point this, then how do we find out the tangent? So for finding out the tangent, it is very simple. It can be approximated by finding out x plus dx, right? If this was x, then this is x plus dx, delta x, right? So find out x plus delta x, and the corresponding if this is x, then you'll have the corresponding y, which would be f of x, right? So there are these 2 points. X plus delta x should be this one, and the point right here that you have, it is x plus dx, and f of x plus dx. Alright, so the point is that we need to find out, if we already have x f x, what we can do, we can find f of x plus dx, and using that we can find the slope. Alright, slope would be delta of y divided by delta of x. Alright, and from that direction we will move. So the direction down a point is given by its derivative. You should have some idea about the calculus, which is important here. And this derivative can be found out by the tangent line that you see right here, the red one. And this can be easily formulated by using this expression delta y by delta x. Okay, which you can approximate by computing the point x plus dx, fx plus dx, and fitting a line with x fx. Alright, so then we have some mathematical formulation which involves the partial derivatives, because that's how the gradient descent algorithm works. So what we are doing here, these are the partial derivatives that we are computing for this error function, which is j w0 w1. Again, we are keeping it very simple by considering only one independent variable, which is x. And then this whole expression that we have, which is based on w0 and w1, needs to be differentiated in terms of w1 and w0. That's the reason we are doing the partial derivative. And then this will involve finding out the partial derivatives and then equating that to 0 and applying the classical calculus approach to find out the maxima and minima. Okay, so if you do these things, you equate that to 0, then you will ultimately find the values of w0 and w1. Okay, so that's the symbolic way of computing the gradient, which we have to find out so that we can determine in which direction we have to move in order to optimize, in order to find out the global minima for our error function. Okay, so here we have these constants like 2 and 2n, just for and so that we can simplify the ultimate result. Alright, so now the important thing that we need to learn or keep in mind is about the gradient descent algorithm. So what do we do in gradient descent? In the gradient descent, we want to find out the slope in which direction we have to move so that we finally reach to the global minima. Okay, and we want the global minima for our error function, which is j of w0 w1. So how do we update each w, right? So wj, here j is for 0 and 1 because our y that you have, y is w0 plus w1 times x, right? So w0 and w1. So what do we do here? We need to update w, right? So you start with any arbitrary wj, w0 and w1, and you want to reach to the w0 and w1, which is the optimal, which will give us the lowest value for the error. So this expression we use where you update the previous value of w j, so you can have, let me write that for w0 the same would apply for w1 also. So you'll update w0 as w0 minus alpha times, then this partial derivative you will do in terms of w0, and this is j w0 w1. You know what is j w0 and w1, this is right here. Okay, so that thing you have to use, and hwx that you have right here, I wrote that as y. That's the same thing. You need to minimize it. And how do we minimize? We minimize that by taking this step. What's the step? You need to update the weight that you have. w0, we are updating w0. The same you'll follow for um, w1 also. You can have w1 is equal to w1 minus alpha times partial derivative in terms of w1 of j w0 w1. Alright, so now this is how you will be doing the gradient descent. And an interesting thing that you need to keep in mind is the formulation of j. So pay attention to this thing because it is very, very important, and that would relate to our next concept that we will discuss. It's about the formulation of j. So the j that you compute involves this computation on all the data points, right? How do we compute j? It's a summation over all the data points. So for one step movement in the jth direction, it will involve the computation on all the data points, which is an overkill in gradient descent algorithm. So this is important. One more time. I hope you got this expression, like how we are updating the weight, jth weight. So you do that as wj minus alpha times partial derivative of the error function with respect to the corresponding coefficient. Weight or coefficient, that means the same thing. So in this expression that you have, which you can see right here, this involves the computation of this error for all the samples that we have in data. So for one coefficient update, one step of update in a coefficient, it involves this computation of the error for all the data samples, which is a bottleneck. All right, and it sometimes slows down the convergence because of the gradient descent. Okay, so for that we have a remedy. We use a different version of gradient descent. We'll get to that later, but let me tell you about this alpha. uh, Alpha is a parameter which we call as the learning rate, or alpha is a learning rate parameter. Learning rate, this determines how fast you can converge to the global optima. If you keep it very, very small, then the movement would be slow towards the global towards the optima or the global minima. And if you keep it very fast, then, well, chances are that you might converge fast, but it's also possible that because of the bigger step, you might miss the optimum. Okay, so now, yeah, as you might have seen that we do need a lot of calculus to understand these things, but good news is that I did not go in the depth, and you don't need to cover that much unless you are interested in finding about it. So here we have some points about the minima, like how do you know that whether we have found the minima or not. So if the function is given to you, you need to find the double derivative and check whether the double derivative is 0 or not. If you get the double derivative is as 0, you get the maxima or the minimum. Alright, so this point is interesting here, that the gradient descent search can get trapped in local minima only if you have non-convex function. As long as your function is convex, you are good. So in our case, the error function that we are using is convex, so we will always get the global minima. But if the error was non-convex, then there are chances that we might get trapped in the local minima, which is not a good news. So here we have an example of a surface or a function that has local minima as well, right? So I will assume that this is one local minima, that's another local minima, probably this is the global minima. So it depends like where from you start. So if you started from here, right, so I mean, in these gradient descent algorithms, we need to start with some random weights. So if your random weight search started here, then you will follow the gradient descent, you'll follow the tangent here, the steepest descent, then it will take you to here already, and you'll be trapped right here. There's no way coming out of it. Whereas if you are lucky, you started from here, followed the descent, and every time you were following the right path, you will converge to the global optima. But if you're unlucky, you might get trapped in the local optima. And why is that happening? That is happening because the surface that you're looking at is non-convex. If you have non-convex surface, then you will get trapped in the, there are chances that you may get trapped in local optima, local minimum. Alright, so now the learning rate, right? So that alpha that you have in the gradient descent is called the learning rate, and it's an important parameter to tune in your optimization process. So if you take a very small steps, right? So if your alpha is very small, you will converge to the global minima, but that will be slow. Okay, so it will be slow convergence, right? So if you're fine with the slow convergence, I'll say okay, go with the smaller learning rate. But if you take you should not go to the other extreme also. You should make it slightly bigger so that your convergence is faster to the optima. But if you make it too large, like something like this, right, so you might experience something called as oscillations, right? So you might overshoot the goal. You came here and then you're you were jumping like this. Why so? Because of the learning rate, your steps were too big. Here the steps are small, so you are moving in the right direction. You are going to the global optima. You are not overshooting the optima. And when will you overshoot? You will only overshoot when your steps are bigger. From here, in place of going to this point, you will go to this point, right? So that can happen. So we need to be very careful about the the size of the learning rate. Alpha should be a decent value, right? So that's the discussion. What should be the right learning rate? So we need to for that thing, I mean, in order to come up to a value for the right learning rate, we should monitor the loss function. Okay, see whether the loss function is going down or not. So if the loss function is going down, that means you are on the right track. So if the progress is too slow, loss function is decreasing, but it is very slowly decreasing, you might adjust the learning rate by multiplying that by a constant. So if you do it 3 times, then from the next step it should probably go faster. Okay, and then see, is it really working out or not? And similarly, if you want the error function to go down, right? So in case this j is increasing, j is increasing, it means that you are overshooting the optima. All right. So if that is the case, then you need to reduce your step size. You need to reduce the learning rate. So how will you reduce? You can follow the same approach. You can, but you need to divide in this case. You cannot multiply because already you're jumping. Your step size is big. You need to reduce this step size. And how can you reduce? You can do it by 1 by 3. All right, and you should not worry about all these things because I believe that these are all implemented. So the library function which we are using would be already taking care of it. Alright, so now the last point that we have is about an interesting variant of the gradient descent called stochastic gradient descent, right? So if you remember, right, let me take you back here. When you're doing the partial derivative, to update each coefficient w0 and w1 until you converge, this has to go on till you converge. Okay, so there will be a criteria that you will have to impose to find out, okay, I converge now, I don't want to move further down. So that we should not worry right now. We should only know that it has to converge. Will stop only when the values have converged. So if it does not converge, then you'll have to keep updating these coefficients. And for this coefficient thing, you have this learning rate, and then you are doing the partial derivative of this error function. And this error function involves the computation on all the data samples, right? You need to compute this error for all the data samples that you have, which is not a good news. So evaluating the partial derivative takes time, linear in the number of examples for each step, right, which will slow the process a lot. Now there is a heuristic behind stochastic gradient descent. The heuristic says that in place of using all the data samples, if you only use a few examples to estimate the derivatives, right? So don't use all, and maybe use 5 of them, 10 of them. It is up to you. How do you find it out? Just randomly sample some 5 or maybe 4. It is your call. Samples from the data, and using those samples only, compute the error function and use that in the partial derivative. Okay, and move accordingly. Okay, so this stochastic gradient descent algorithm is used a lot. That's what people prefer using. All right, so what is the message here? Now optimizing, what we should be doing, if you optimize the learning rate, and you know the batch size means number of samples to use from training data. Okay, for J. So if you could properly pick the learning rate, which is alpha, and you properly pick the batch size for gradient descent, then it will lead to a faster optimization if you have the convex function. Okay, good. So now there's another interesting thing. So last 2 slides of the lecture are based on that. The number of features, right? So how many features are good for linear regression problem? Should we use all the features, or should we be careful about the number of features? So the answer to that lies in the Occam's razor. So providing a rich set of features to regression is good, but remember Occam's razor. That means the simplest explanation is the best. So what happens actually is that ideally what we should do, we should only pick those features which are strongly correlating with the target, and we should learn, we should come up with the linear regression using those features only. And if we have very small number of features, we might use all those features for our linear regression problem. Okay, so ideally our regression would select the most important, right? So that's what I was saying. It will select the most important variables and fit on them. But our objective function only tries to, okay, so this is about how our optimization works. So the point is that the way our objective function, or the cost function, has been formulated, if you do not take care of the features, then it will try to fit all those features, right? So we do not have any intelligence in the current cost function to take care of feature reduction, right? It will consider all the features that you given, which is bad. It will try its best to consider all those features and come up with a best fit, which is not good. So what has been done, this concept of regularization is very popular, where in the optimization function, so this is the optimization function which has been um, modified. uh, Optimization function, objective function, or the loss function, or the error functions. There are a lot of terms. Okay, error functions, because error function JW, right? So we had it, right? We had this expression. What people do using regularization, they add another term, and that's the term that they have added. So this term has lambda, okay, and then they have uh, lambda is called regularization penalty, I should say. Yeah, it's a regularization parameter which will determine how much weight do you want to give to regularization. So what is regularization? Let me explain that to you. If you don't have this term, then it's this normal cost function which we were optimizing. Now with adding this term, which is lambda times square of the coefficients. Okay, sorry about that. Wait a second. I should get that. What is W, right? W is the coefficient. Coefficient. Alright. So what this expression is saying, it is saying that let's have another term which is lambda times sum of square of all the coefficients, right? So this summation that you see is going from 1 to m. What is m? M is the number of variables that you have. Alright, so with this formulation, what will happen is that when you try to minimize JW, you have to minimize, right? So when you're trying to minimize this error function, anyway you will minimize the residual. This is residual error. At the same time, you will be minimizing these coefficients as well. So you should wonder why W square. For the same reason, we want to ignore sign. You want to ignore the sign, so you have to square the coefficient. Square that up, sum that up, and multiply that by lambda. Okay, what is the role of lambda? Well, lambda will determine your focus, like what do you want to emphasize more. Do you want to emphasize less number of features? If that is the case, then your lambda should be higher. If you keep lambda is equal to 0 or very low, then this term will have no impact on your optimization, and this optimization will work just the way it was, right? But if you have a higher value of lambda, that means even this term, which is the summation of the square of these coefficients, will have a role to play. Okay, and this is very important. With the higher value of lambda, what will happen? It helps in generalization also. It will overcome the overfitting problem. Okay, and a lot of features that you have, or a lot of variables that you have, which are meaningless for the regression problem, which does not correlate strongly with the target value, they will be anyway ignored. These values will boil down to 0 in the optimization problem. Alright, so that was it. I will stop right here. Good luck. Bye bye.